Kudzu is a very fast-growing invasive plant from Japan. It's a fast-growing weed, so there seems to be a theme of plants in this space, so that's our plant. So this is going to be a protocol in the partially synchronous blockchain-style consensus model, same model as PBFT, really. We have n parties, less than a third are corrupt. Liveness means we only have liveness during periods of synchrony. Safety, always. Thank you. And I'm going to introduce you to Kudzu by way of two other protocols. So the first protocol is, that I'll talk about is Simplex. This is a beautiful protocol from a couple of years ago. It's simple, and it's objectively simple. And it has optimal latency, only if you just think about latency, at least in a theoretical sense of just network hops. A big problem with it is its communication complexity is pretty bad. On the one hand, if you take it like completely literally, if you like read the paper and see what's in there is the leader in every round has to broadcast the entire blockchain back to the genesis block to every other party. And then every party then echoes the entire blockchain to every other party. So that's clearly, I mean, that's what's in there. And so it takes just a little bit of thinking to see how you would make something slightly better than that. But even if you do that, the communication complexity is pretty bad in the sense that there's this leader bottleneck where the leader is broadcasting a block to all parties. And it's well known that this causes problems. Dispersed simplex is a little thing that I wrote a couple of years ago as well, inspired by simplex and some, at least by the name dispersed ledger. I proposed adding some features here, so it's still objectively simple, and it has the same latency as simplex, and it has good communication complexity. And good meaning like small, and also so there's no leader bottleneck, and it's balanced. So every party is including the leader is sending out the same amount of data on the network. And this ignores things like all-to-all communication. If the blocks are big enough, then the all-to-all broadcasting of certificates and signature shares doesn't really matter at all, right? So all of this whole line of work about linear complexity is kind of not really relevant to practice, at least for large enough blocks. And then Kudzu is recent work which I did with these guys, and that's the end point of today's discussion. So basically, this has all of the nice properties here, plus there's an optimistic fast path which gives you even better latency under optimistic conditions. Okay, so quick introduction to simplex. I'll just give you kind of a graphical view of like what the blockchain or the block tree looks like. So we have slots here, or call them views or rounds, whatever you want to call them. So I've started off here with like a snapshot in time where I have one certified block. So there's a BC, a block cert for it. And it's also been finalized. Okay, so this is our starting point. Probably lots of other stuff happened back here. But then, okay, in the next slot, the leader proposes a block, and it gets certified eventually. Say the next slot, nothing gets certified, but a timeout occurs, right? So we're in the partially synchronous model, and there's a built-in timeout threshold that can trigger. And if enough people vote for a timeout, you'll end up with a timeout certificate. So in the next round, say, the leader proposes another block. And the rule is, blocks have to point to a predecessor. And you can point to your previous predecessor. You can point arbitrarily far back in the chain. But the rule is you're not allowed to, if you skip a slot, you can only skip it if there's a timeout certificate there. And the leader doesn't broadcast the timeout certificate. It just knows that if it sees the timeout certificate, everybody else will eventually see a timeout certificate. So they'll vote for his block when they see the necessary timeout certificates. So now, say what happens in this round is that it can very well happen that a block gets certified, but a timeout certificate is also generated. That can also happen. In the next slot, I've shown you again here a block that gets certified. It actually jumps over 2 slots because there's 2 timeout certificates, so it can do that. And say in this round, we might actually get a finalization certificate. Oops, I went too far. Finalization certificate. And as is typical in these types of protocols, this implicitly finalizes everything on the path back to, well, and including what was previously finalized, right? So this guy here gets implicitly finalized. Okay, so that's simplex at a high level, slightly lower level. In each slot, there's like 3 rounds of communication. First round, leader proposes a block. Second round, there's an all-to-all voting that occurs. So all parties, when they receive the block, will send everybody else a vote for that block. And we can implement that rule that you only vote for a block if you've seen timeout certificates for any skipped blocks. That'll automatically enforce this skipping rule. And then each party will finish the slot when either it sees a block certificate or a timeout certificate. Then it will move on to the next slot. In parallel with the beginning of the next slot, though, there's a voting round, a second voting round of finalization votes that will be used. So and the rule is you only vote for finality on a block only if you didn't vote for a timeout. And that automatically gives you a nice quorum intersection property because you'll never vote for a timeout and a finalization. No party will vote for both. And because of that, these buttons are a little bit tricky. You can't get both a finalization certificate and a timeout certificate in the same slot. And by the skipping rule, that means something that's been finalized can never be skipped. And that's what gives you safety, basically. That's the whole argument for safety. So that's simplex in a nutshell. I love it because it's so simple, again, objectively so. And I think that if you're going to teach one partially synchronous consensus protocol, this is the one you should teach. And I didn't invent it, so I'm just saying it's just really cool. What's that? I'm just saying this is objectively the simplest, most elegant protocol there is. You can't hide from the truth. Okay, so dispersed simplex is just a simple idea that I cooked up, just kind of obvious, and I don't even think it's that great. But so I said the leader can become a bottleneck in practice. So the obvious way to eliminate that bottleneck is to use erasure codes. So if the block has data, there's some metadata, but then the transactions themselves form some big, 4 megabyte block of data. So you're going to erasure code that up into n fragments. And then the leader is going to include in the proposal message just the fragment for the ith party, so just one fragment. And then each party, when he votes, is just going to include his own fragment and broadcast that to everybody. And so by the end of the voting round, you've already, when you certify the block, you guarantee that there's enough good parties holding fragments and who broadcast them that everybody will eventually be able to reconstruct this block. And then each party, the observation then is that each party, and if you're careful about it, including the leader, each party, including the leader, is just going to transmit total number of bits equal to 3 times the data size. So it gives you kind of perfectly balanced communication. Okay, there's this 3 here, which is a little bit annoying. It'd be nice if it were 1. There's a variant in this paper with a stable leader that actually gives you 1.5. So that could be nice in practice. And again, I'll just emphasize, no leader bottleneck, right? So in practice, that's like the whole thing, right? I mean, so the whole motivation for looking at DAG-based protocols and CAR-based protocols, I mean, I do appreciate the fact that the whole hangover problem is an interesting thing, that there are clear trade-offs here. But the motivation for DAG seemed to be that, we want to have balanced communication. Well, one way to have balanced communication is to use a balanced data dissemination protocol and a leader-based protocol. So you don't have to trade off leader for leaderless just to get balanced. There are other reasons, though, for like hangovers to look at leaderless protocols. So like if nothing else you get out of this talk, that's the main thing. Like leaderless protocols don't have to have leader bottlenecks. End of story, right? So it's kind of just kind of some misinformation that's maybe slowly we're slowly getting rid of. So Kudzu, what is Kudzu? We want to add a fast path, right? So here we have, between the time the leader proposes, there's a total of 3 network hops: propose, vote, and finalize. And it would be nice if we could already finalize at the end of the voting round. And there's a whole long history, somewhat sad history of buggy protocols proposing these fast paths, many of which have been broken, repaired. Dare I say, even hydrangea. Where's the hydrangea people are here? Yes. You represent them? So there was even a liveness bug in the initial version of their thing, which they can be complicated protocols. They can be complicated protocols. But Kudzu, yes, is simple. So the basic idea though behind all of these protocols is that we want to get some kind of a fast finality certificate, which is just going to be comprised of sufficiently many properly defined votes. Right? If we see n votes, then we should be able to finalize this sucker, right, without waiting for anything else, right? Well, okay, that's the basic idea in all of these protocols. And if we can do that, then of course we can finalize right here without waiting until we get over here. The problem is, the way I've defined, if that's the only change I made to simplex or disperse simplex, you could end up getting a fast finality certificate and a timeout certificate at the same time. Because everybody's broadcasting, say, a vote, but then these votes get stuck in the ether for a minute, and then everybody generates a timeout vote, and now you have n votes for timeout and n votes for a block, and well, there's nothing that you can do to stop people from seeing both of those, right? So this breaks the whole safety argument, right? We weren't supposed to be able to finalize and get a timeout certificate at the same time because that allows people to skip, that would allow people to skip finalized blocks. Okay. Solution, partial solution. Okay, well, let's change the logic so that we vote for either a block or a timeout, but not both. Well, then automatically we can't get a FFC and a TOC, right? But then the problem with this is liveness, huh? Well, there's no guarantee that you do anything then, right? Half the people vote for timeout, half the people vote for a block, and you don't form a certificate for either one, so you don't get out of the slot. Okay, so then we have to introduce complicated progress certificates and other, no, we don't do that. We do something very simple because that's the main thing, right? So the idea is that we're just gonna, if after we vote for either a timeout or a fast finality certificate, I mean, we'll move on if we get one of these, as usual, but we'll also cast some secondary votes under the right conditions, but they're simple conditions, okay? So, and these are secondary, the only weird thing is, these are secondary votes, not to be confused with these initial votes, right? So you can't get a fast finality, so if I vote for something else, you can't get a fast finality certificate out of those things. They're not in the same category of objects, right? So they're just secondary votes. So there's 2 different types of secondary votes. One is if I'm stuck here waiting, but then I see a bunch of votes. I'm not going to tell you exactly how many, but I see a bunch of votes for a block. And it's a block that I didn't vote for before. Maybe I just voted for a timeout before. Or maybe I voted for one block because the leader was malicious and is equivocating, but I see many votes for another block. I'm going to jump on the bandwagon and vote for that one too. Okay? So, and that'll be my secondary vote. And the other secondary vote that I can cast is a secondary vote for a timeout. If I see a very simple yet carefully defined notion of a diversity of votes. If I see that there's a diversity of votes, then I will vote for a timeout. And the idea here is that this condition here is defined in such a way that I can't vote for a timeout if somebody was going to fast finalize. But it's just a simple inequality. I just look at my votes, I count them up, and if I see the right number of votes of a certain type, I'll just vote for a timeout. So that's it. So there's no like fancy progress certificates. This is literally just saying, oh, I've seen this many votes of that type, vote for a block. I've seen this many votes of another type, okay, vote for a timeout. And that's it. So I'm not going to go into more of the details here. You can read the paper. It's all very simple. So in conclusion, Kudzu is simple like simplex. It has optimal latency like simplex, if just in the pure theoretical counting the number of network hops version. But also, like dispersed simplex, it has good and balanced communication complexity, which means when you take into account the effect on delay of both bounded bandwidth, network bandwidth, and network delay, network latency, you can still get very high throughput without sacrificing latency. And again, each party, including the leader, is just going to transmit the same relatively small number of bits. And it also adds a fast path. So in detail, it's this. We've seen this, this expression before today. You have F corrupt parties, this extra parameter P. And if you'll finalize in time just 2 network hops if at most P parties are corrupt. And otherwise, you'll still, just as normal, finalize in 3 network hops. And that's it. I have plenty of time for questions.
So these protocols obviously get simpler and simpler. That's clear. But like, why is this simpler than in PBFT when you, because like voting for a view change is like voting for a timeout. We can kind of make that relation, or you do a vote.
Well, and of course, I didn't really talk about view changes at all here. So
that's a timeout. That's a sort of a timeout certificate where something happens. Yeah.
Yeah, but if you get it right. So first of all, there's different ways of implementing this. You can actually have a view change every round. So it's more like a hot stuff kind of style where you can change leaders in every round if you like. There's no special sub-protocol for doing that. And in terms of comparing to PBFT, I mean, PBFT has a, you know, quote unquote, notoriously somewhat complicated view change protocol. This is just you collect a timeout certificate, then you move on, and there's nothing else that you need to do. The only thing that, and it's all taken care of, and this is simplex, right? It's all taken care of by the timeout certificate, the interaction between the impossibility of getting timeout and finalization certificate and the skipping rule that doesn't allow you to skip over, that only allows you to skip over slots where a timeout certificate is formed. And this like drastically simplifies the whole view change business so that it becomes quite easy. In the skipping rule, do you need to provide multiple timeout certificates? Right. So, no. You don't. You as the leader, you don't provide any. Okay. You just go on with firm in the knowledge that if you've seen it's because all these protocols have the property. If I've seen these 5 timeout certificates, then you will see them too. That's just the way that everybody's echoing around these timeout certificates. So there's a fundamental property is if any honest party sees a timeout certificate, they'll broadcast it and every other party will see it immediately.
I see. But the individual parties do need the whole sequence of skipped slots, timeout certificates.
Yeah, they'll have to remember them. The leader doesn't broadcast them, but they'll store those. So for every slot, you'll store a block and maybe a timeout certificate, one or the other or both. And yes, it's important that you just don't forget those things.
On the networking side, with the leaderless setup, is there an optimal number of shards or kind of network participants that you send components to? Or is there an optimal network topology? Because for leader-based protocols, what I've noticed is that stake weighting in a tree with, I guess co-located node is probably like the easiest way. I'm just curious.
This only really makes sense in a setting where you have n equally weighted parties talking to each other over point-to-point channels. If you have overlay networks, if you have weighted stake, I don't even, maybe people can tell me, I don't know if you have weighted stake, I mean, actually Alpenglow does this, so maybe they'll talk about this. If combining weighted stake with sharding is actually a complication that Solana has solved, I guess, so that's something that maybe Roger will talk about next.
I think to Marco's question, the difference with PBFT, which might be a moot point in practice, but is that here, if you have like bad network conditions, you can keep not making progress, meaning you don't commit anything, but the state you have to keep grows linearly because you have to keep all those timeout certificates. And so your state is unbounded in some way, right? Even though you're not making progress. But it's probably not a big deal in practice because you're not going to have super long periods of no progress.
I mean, in practice, you would probably do something anyway, like start increasing your timeout interval so that you do start making progress. But yeah, there's a number. Simplex isn't the only protocol with this property, but yeah, if you're saying that in some protocols like PBFT, you might not finalize everything. Wait, is that true?
So
But you'll say you'll be building up some state that you can finalize?
So in PBFT, even if you have a really long period where the network is asynchronous and you can't finalize and you keep starting new views that don't make progress, you only remember a constant amount of information about all those views. Whereas here, you remember a linear amount of information per view that doesn't make progress. Right?
Yeah, okay, that's fair, yeah. That's a fair criticism. I don't know if it's a deal breaker, but it's a fair criticism. I don't know, yeah.
We have to make the protocol more complex to deal with that.
Yeah. Darn it, well, okay.
Cool.
Implementation.
One more question.
Before I ask, I'll just say I'm also a big fan of Simplex. You've been working on Simplex, like thinking about and researching into Simplex for some number of years now, at least from your dispersed Simplex work into this. I'm curious if there's a particular direction you think it takes from here, like the Simplex style of approach, like if you have new, twists and turns following Kudzu, following all this work you've done in this direction.
I don't know, but there's okay, I'll throw out one open question here, is that, which we don't know how to solve really, is like, for this basic dispersed simplex without the fast path, you can, with a stable leader, you can reduce this constant 3 to 1.5, so you can get better data dissemination rates. Here, I don't know how to do that. So there's one little open, it's not a visionary, directional type of thing, but that's like the one open question I can see. Yeah.
Cool. Let's thank Victor one more time.